Let's recall our definition of electric field associated with a source of charges. So what I'll do is I'll draw an area here which I'm going to refer to a source of charge. And let's pick a point P up here. And we saw that if we place a test charge, Q test, at point P, then we defined the electric field at the point P to be the force on that test charge at the point P divided by the test charge. And what this enabled us to do was to be able to associate everywhere in space electric fields of this source. So if we were at different points, the electric fields at these different points, P1, P2, point in different directions. So we would end up having an arrow at every point in space. And we learned how to calculate this electric field for a variety of different types of sources, point charges or sources with symmetry. But the important point was that if we place a charge Q at P, then we know that the force on Q is just Q times the electric field of the source point. And that was useful for us because now we could write down Newton's second law to be able to get an expression for the equation of motion of this object. And on this side, the force is just the charge, Q source P, equals the mass of the charge times the acceleration of that charge. And that was the reason we chose the electric field. Now, in mechanics, we talk about Newton's second law, but we also have our energy principle. And we want to introduce an analogous idea to handle energy concepts. So once again, let's consider a source. And this time, we want to consider 2 points in space, A and B. And instead of, what we'd like to do is imagine that we're going to move a test charge, Q test, from A to B. So we move our test charge from A to B. And our test charge is in the presence of this electric field of the source, E source P, if this is the point P, but there's an electric field of the source everywhere. And now what we'd like to do is define a new concept. We'd like to say that it's called electric potential. Now, we have to be careful here. It's not potential energy, but electric potential difference. And the way we define that concept is as follows. The electric potential difference between 2 points A and B is minus the integral from A to B, that the force that this test charge would experience in moving in the presence of this source of charge, dotted ds. So this is the negative of the work done by the test charge, but again, we divide by the test charge. Just like we have the electric field of a source, force divided by test charge. So this quantity inside here is the electric field of the source. And so now we have a concept of that is completely independent of our test charge. It's the minus the integral of the electric field of the source will give us a quantity which we refer to as the potential difference between 2 points in space. Let's now calculate the potential difference for some sources that we've been using Gauss's law for. Let's take our first source to be 2 thin, infinite parallel plates. So we have plus sigma and minus sigma. And let's take this to be our j hat direction. And we'll even choose a y-axis here. Here's y equals 0, y equals d over 2, and y equals minus d over 2. Now, from Gauss's law, we saw that there's an electric field from these sources that points down. And in between the plates, the electric field from the source was minus sigma over epsilon naught j hat. And we found that from our Gauss's law calculation. And so now we want to calculate the potential difference. And let's take the potential difference from the upper plate. So imagine we have a point B up there and a point A down here. And we're going to look at VB minus VA. And our definition was the integral from A to B of the electric field dot ds. Now, one of the things that we have to look at is to make sure that we have a good coordinate system. And what path should we take? We know this result is independent of the path, and so I'll just consider a straight line path. And ds is going to be dy j hat. Now, once again, we don't put a plus or minus sign in here. You'll see the endpoints of the integral will tell us that. We have the expression for the electric field. And so the potential difference, V at y equals d over 2, that's B, minus V at y equals minus d over 2, that's the lower plate, is equal to the integral of this dot product. J hat dot j hat is 1. And so we have another minus sign, minus sigma epsilon naught dy. And here we're going from y minus d over 2 to y equals d over 2. And this is a straightforward integral. It's just equal to d. The two minus signs come out, and we get sigma d over epsilon naught. And if you'll notice, this quantity is positive. And that tells us that the upper plate, the positive plate, is at a higher potential. This is a higher potential. And the lower plate, this is at a lower, the negative plate is at a lower potential. And even notice that the electric field in this example is pointing from higher potential to lower potential. So here's a classic example of a simple calculation involving potential difference for one of our basic Gauss's law superposition examples. Now let's consider another potential difference for one of our symmetric charge distributions. So let's take a very thin spherical shell of charge plus q and radius a. And let's take an outer shell with a charge minus q. Both of these charges are spread uniformly over these shells, and that's a radius b. Now, once again, from our Gauss's law calculation, we know that the electric field is 0 inside and outside this configuration, and it points from the positive plate to the negative shell. And from what we expect that the potential function will be higher on the positive as opposed to the lower. So I want to do this calculation in the following way. So let's take the potential difference between where the positive charge is and where the negative charge is. So I'm going to integrate from, I'm going to integrate from the outer plate, outer shell to the inner shell. And I'll choose a path, once again, that's going to go straight. So this is going to be my path, divided up into a bunch of pieces. And I'm going from, now I'll go from the plate, the outer one, to the inner one. And I'm just denoting it by the radius of E dot ds. So once again, we have to set up this integral. And recall from Gauss's law that when you're outside a uniform shell, it looks as if all the charge were at the center. And we found that the electric field in the region between the plates as a function of r is just k charge on the plate divided by r squared r hat for the region a less than r less than b. Now, here comes the interesting thing. Again, we'll write ds in a coordinate system in which our r hat vector is spherically outwards, the radial vector spherically outward, and we write dr r hat. Now, many times people will be tempted when they see this path to put a minus sign in here. But remember, dr is just a quantity that can be positive or negative, determined by the endpoints of the integral. And so what we get is that v of a minus v of b is minus the integral from r, we're going from b, let's make sure we have that right. We're going from the outer shell to the inner shell. And now the dot product of these two vectors is positive, r hat dot r hat, positive quantity. And there's a minus sign overall on the outside. So we have a one-dimensional integral representing by taking a path just in one dimension. And this, again, is a straightforward integral. dr over r squared, the integral is negative 1 over r. The two minus signs cancel. So we get kq over r squared over, putting the endpoints here, of 1 over a minus 1 over b is this potential difference, VA minus VB. Now, let's just check that our calculation is correct. What did we expect? There are different ways to think about it. The electric field points down to lower potential, so we expect this surface to be at a higher potential. It's a positive charge, so that kind of reinforces that idea. And if A is less than B, then 1 over A is bigger than 1 over B. And so we see, as we expect, that the potential difference here is positive. And indeed, our inner surface is at a higher potential, and the outer surface is at a lower potential. And there's the case of two concentric spherical shells that have opposite charges. We'll have a third potential calculation, and this time we're going to look at the following distribution of charge. We'll take two cylindrical shells. So here's our outer shell. We'll call this one a radius b. And we'll have an inner shell. I'm going to put that inner shell in a different color just so we can make this look a little clearer. And we have inner shell, and our inner shell has radius a. And on both of these shells, what we'd like to say is that on the outer shell, the charge will be, these are going to be infinite cylindrical shells. And on the outer shell, we're going to have its charge will be distributed uniformly with a minus lambda. And on the inner shell, charge will be distributed uniformly with a positive lambda. And in our Gauss's law calculation, we saw that there was an electric field that pointed from the inner to the outer. It was 0 in this region and 0 in that region, only non-zero between these shells. And in that region, if we choose an axial radial direction, pointing away from the symmetry axis, then we have the electric field lambda 2 pi epsilon naught. And it went like 1 over r hat. And that was our electric field, and that was in the regions A less than R less than B. And so now we want to calculate, again, our potential function. And again, we expect that the positive shell will be at a higher potential. So we'll calculate V of A minus V of B. And that's the integral. And this is going to be the integral from R goes from B to R goes to A of the electric field E dot ds. Now again, we need to choose a path. And since we're going from starting at B and going to A, B is the radius of the outer shell, going to the inner shell, we're going to go directly inward. And our ds vector, I'll write it over here. The ds, now we have to be careful here, it's just equal to dr r hat. It is not minus dr. That's taken into account the direction and the sign of the drs by the endpoints of the integral. So when we take the dot product, r hat dot r hat is 1, and along this one-dimensional path, our integral reduces to simply the integral from r goes from a to r goes from b of the charge density, 2 pi epsilon naught, and we have a dr divided by r. And once again, we have a straightforward integral, a natural logarithm, and this is lambda over 2 pi epsilon naught. I'm going to keep the minus sign, natural log of b over a. I'm sorry. We are going from b to a, so my endpoints are the wrong way. We're going from b to a, and so this is the natural log of a over b. Now, that's a good thing, because if a is less than b, the log of this quantity is negative, and so we have two negative signs in here, and so we can conclude that VA minus VB, and by the way, if we flip those, log of A over B is equal to minus log of B over A. That's one way to get rid of that minus sign, and we can see very clearly now that this quantity is positive. So there's the calculation for what we would refer to as two infinite cylindrical shells.